Ville Kyrki from Aalto University, talking about both reinforcement learning and the autonomous AI program of FCAI.
Thanks. So, good morning. My name is Ville Kyrki. I'm professor here in Aalto University, and leading the intelligent robotics group here. And today I'll talk about one of our recent papers, or actually soon to be published papers, on meta-reinforcement learning for synthetic adaptation. But before I go to that topic, now this one, I have to turn it on. Now, yes, first briefly about the FCAI Finnish Center of Artificial Intelligence Autonomous AI program, which I am coordinating. So this is just I'm trying to not waste too much of your time, but I want to very briefly give you the gist of this. So the Finnish Center of Artificial Intelligence, the research activities are organized in research programs. Currently there are 7 of them. And the research program is a kind of entity that consists of multi-research group doing fundamental AI research with some shared research agenda. And autonomous AI is one of these. I want to just take this opportunity to do a little bit of this autonomous AI, because autonomous AI was almost at the end of the list, and the reason for that is that because it's just starting. It was not one of the original 5 research programs, but it's a new one that started a little bit later than the others. So as a background, the autonomous systems are increasingly reliant on AI methods. So in practice, it means that when we are looking at, for example, autonomous cars development, both the companies as well as then the other players on the market are increasingly looking at AI or machine learning, especially machine learning related techniques in developing those methods. Of course, myself, I'm not a believer on end-to-end autonomous car, that we can throw in all the percepts of sensor information from a car into some great big neural network that will then spit out the driving commands, even if we have a great kind of proof of concept in our own brains that this can be done. But I'm not really believing that will be how in the next few decades we'll see systems working. But for sure, machine learning and AI will be an important component in those systems. So some of the challenges when we look at autonomous systems are that when we put something like a car in operation, it really needs to operate there long term. It's not making a single decision that's independent of all the future decisions. It needs to take into account the nature of the system, which is kind of living in its environment, affecting also its environment. So the way it acts, the environment reacts to that, and it may affect the other players in the environment, the actions of each agent. So the challenge there are really these long time horizons. Another thing that when we put AI in physical systems is obviously safety, which relates in particular to the questions that if we want to do some exploration in the world, if the system needs to try out things in the world, ensuring the safety of this learning system in those kind of environment is really difficult, especially because it needs to try something new. In order to get more interesting data, it has to do something it has not done before. Otherwise, it can just memorize what it did before. But in order to learn new things, you need to get new experiences, and getting new experiences requires going where no man has gone before, basically requires trying things that where we cannot be easily sure about the safety of those actions. So for that reason, the autonomous AI program is organized in terms of 2 research themes. One is long-term decision making, where our, let's say, scientific aim is to increase significantly the temporal horizon of goal-driven decision making. So that means that when we have a system that has a particular goal, how can we plan longer horizons in systems, in real systems where there is uncertainty in the dynamics of the world. So that means that we are not playing a game where we know exactly the rules, as well as we are also looking at where the complexity of the environment is large, and we don't know exactly the environment. So that will consist of being able to build those temporal models for system dynamics that act in long term and take into account uncertainty. Data efficient models, so basically with limited data we have to be able to fit the models or estimate the models, and then also do efficient planning in these models. So basically, typically the traditional way of seeing planning under uncertainty would be using partial observable Markov decision processes, but by definition they are p-space hard, so basically they are computationally not, they are computationally extremely challenging, meaning that we have to be able to make some simplifications in order to solve them, the computational problems. The other part is the safe learning, which basically, okay, here we can see what may happen if the robot is not necessarily safe, or in this case the robot is safe. Sami here is smiling after the robot hits it. But in practice, we don't want to have these kind of systems, or it's very hard to build systems that move in the real world and make them intrinsically safe. So in that case, and like I mentioned already earlier, exploration in reinforcement learning and guaranteeing safety there is one of the basic things, but also another thing when we want to learn complex systems is that we often use simulation. And in those cases, when you use something in simulation, this simulation always differs from the real world, and we have to somehow be able to bridge that gap between simulation and reality. And that's also the topic of my today's talk. So I want to mention one thing, that there are many other research programs in FCAI that are related, especially the simulation-based inference, probabilistic models, and deep learning programs that are also very much contribute to the same area. The autonomous AI program is in ramp-up phase, so the research agenda is there already, but it's under further development. And if you are interested, feel free to contact me and I can tell you more about the program. I want to give you one more slide. Also in Aalto, there's a new Aalto Center for Autonomous Systems, which is the launch event is in April the 1st this year, that considers autonomous systems not only from the AI perspective, but in a much wider context. And this one will be launched in April. But now to the interesting part of the talk, hopefully, which is about our recent paper that was recently accepted to IEEE International Conference on Robotics and Automation. And this is work of Carol and Murtaza, especially also Ali, my former postdoc, was working on this on meta-reinforcement learning for sim-to-real adaptation. So some of you probably are familiar with all of the words. Not all of you are familiar with all of them, so I'm trying to start from the problem, which is simulation to real adaptation. So when we have, it would be really nice to be able to learn to drive or build an autonomous car from just having some kind of nice car game, train, whatever model you have. I mean, here's a neural network, but there's just any decision-making machine learning model, and then just apply that on the physical system. For sure, there is a gap within this simulated environment and this physical road environment, so we need some kind of transfer learning in order to turn this policy learned in the simulation into policy that can be used in real world. The reason why we are at all interested in the simulation is that the data cost for physical world is really high. So the amount of data we can get from simulation is orders of magnitude higher than the amount of data we can get from physical world. But on the other hand, we still need to gather some data from the physical world, because our simulations are always somehow lacking in in the complexity of the world they model. For example, we may have very realistic graphics in the simulator, but for example, when we consider driving, the driving behavior of other agents, how people drive, for example, is something that we very seldom have good models for in the simulation. So in order to do this kind of policy learning, the typical way is to do reinforcement learning, agents trained in simulation cannot be directly used. So how to address the reality gap? So in this work, we are actually looking at the particular aspect of this problem, which is unknown parameter values. So for example, we are looking in the case where we have modeled all the required phenomena in the problem, like driving, but we have not modeled, we don't know the parameters of those phenomena. For example, we don't know the road surface friction parameters. We don't know other parameters such as how other agents work, whether they are aggressive or very cautious drivers. We don't know some other parameters. We have models for those phenomena, but we don't know the parameters of the models. And that's the primary thing we are addressing here. So to show you, I mean, this is a robotics paper, not a machine learning paper. Here's one of our examples that we are primarily studying, which is a robot hockey. So actually, the parameters we have here are simple physical parameters such as masses and friction coefficients, but even relatively simple phenomena like friction, which you probably learned at high school, is not at all trivial. And first of all, the Coulomb model that we often learn doesn't really work. So actually, in this simple simulation, for example, we don't have a single friction coefficient. We have at least 5 different variables that characterize the friction, even in this example. Furthermore, when we add there more parameters such as masses, location of center of masses, and what we want to do is, of course, learn how to hit the puck with the stick. In order for it to go to any location we want it to go, we have to also, the thing we optimize is the trajectory of the stick and the blade, which is in a relatively high dimensional space. So the reason for that is actually not only that we are looking at the temporal sequence, but that what we are looking is the motions of the robot. We're not looking at the motion of the stick, but we are looking at the motion of the robot, which has in this case, 7 degrees of freedom. So we are looking at the joints of the robot and how should we control the joints of the robot to make the hockey puck go into a particular place. So there's a kind of series of inferences that have to be made or that are intrinsically made or implicitly made in the system. Okay, so now back to from the very practical robot playing hockey. By the way, we are not at all interested in hockey playing robots. This is just an example what we are using here to study the methods. So this has to be mentioned because, I mean, otherwise we just get comments from the people interested in hockey, and that's actually not what we are interested at all. So back to the math. So basically the problem definition. So what we have a problem is that there's a set of reinforcement learning problems that is basically a reinforcement learning problem is a Markov decision process. So Markov decision process is a Markov process where in addition to states and actions, we have rewards that the system is trying to maximize. So rewards that are functions of states and actions. And we are looking not only at a single Markov decision process, but a set of Markov decision processes where the state and action spaces are the same. So in this hockey example, the state space is where is the puck. And the action space is what kind of forces we put in each joint of the robot. We have a reward function, which is basically distance of the puck from the location where we want it to be, and as well as some cost for the action. So we want to minimize the forces or the energy expended by the robot in order to move. We have transition probabilities that are parameterized by the set of dynamics parameters. So this is the part that is different from these models. So because different frictions, the transition dynamics, so executing a particle action, particle state, results in a different distribution of states at the next time instant. Those vary, and those are parameterized by dynamics parameters. We expect that we are able to simulate these dynamics for any parameter, particular parameter value we choose, but we don't expect to know the distribution model. And finally, we also say that what we want to do is we want to learn a parameterized policy such that from any state we can now choose the action we want to do. So this is kind of the setting, and now the problem we want to address is that if we know a distribution of dynamics parameters, so we know the distributions of this tau that describe our, let's say, uncertainty of the friction, we want to find a policy that after a few updates or trials under a particular dynamic condition, so now we have a particular puck there, the particular hockey stick, we want to try a few times, and we want to find the Bayes optimal policy for that condition. In this case, we are not actually looking at the proof of Bayes optimality at all, or we don't start from Bayes optimality, but that would be the goal of the in the best case. What we are looking is a policy that results in a good update in this particular paper. So we are not trying to prove the Bayes optimality of that policy in this particular paper. So that means that we are able to, let's say, in the simulation gather lots of data, but in the real world gather only these few trials that we can use information from them to update the policy. But in order to do anything, to do a trial, we have to have some starting policy as well. And the solution we have consists of basically two parts. So the first part of which relates to latent space modeling, or basically simplifying the policy parameterization. So far what we had, the policy was really the trajectory of the, for example, the trajectory of the entire hockey stick, or the decisions made in order to move the hockey stick. That is high dimensional, and for that reason the number of parameters is very large, which makes it hard to optimize. So we want to be able to do some latent space modeling there in order to find a lower dimensional space where we can optimize the policy in a simpler fashion. Another part of this relates to meta-learning, which is basically we cast this problem into a meta-learning problem. That's another kind of a new thing we are using in this particular context. So what we are, both of these are, the methods are something that have already kind of existed in similar domains, but not in particular in this domain. So first, to talk about the policy simplification, for the reason that even though I think that meta-learning is actually the most interesting part, it's easier to understand in this particular order, at least for me. So instead of learning the full policy, we want to try to learn a trajectory to follow based on a single observed starting state. So basically, we are, instead of trying to think in terms of reactively changing while we are hitting the puck, we are just observing where our goal is, and then we are trying to kind of plan the trajectory or have a policy that can output the entire trajectory of the hockey stick in order that after it hits the puck will go to the particular goal. So there are quite many problems where this kind of, in a way, feed-forward control, where we don't use the feedback all the time, is sufficient, especially in cases where the feedback is very slow to affect the dynamics of the system. So this actually theoretically simplifies the problem to a bandit instead of fully Markov decision process, or basically a multi-armed bandit, or that can be understood as a multi-armed bandit, the entire problem. But the trajectory we want to optimize as U is still high dimensional. So we have a time series of 7 joint values or 7 joint talks. And that time series is still can be relatively long, because the robots are controlled in, let's say 100 hertz, that means 100 times per second, and even if the single hit takes us only a second to do, we still have, let's say, 700 variables we need to optimize. So our output is maybe 700 numbers, which is really hard to predict from, or quite hard to predict from a single goal location. So what we do is we learn a latent space generative model for this trajectory. So we want to learn a latent space, Z, that describes decent trajectories, or describes trajectories that make sense. Trajectories that somehow, at least, where the stick hits the puck in some way and the puck starts to move in some direction. And when we have, if we can get data from that distribution of trajectories, we can try to find a low-dimensional latent space distribution that describes these. And what we are doing here is we are actually using a variational autoencoder, which is a neural network structure that typically is used to basically learn reconstruction models, and this we are learning using that the latent space trajectory. So this is actually just the decoder part of the variational autoencoder that we use. So the nice thing when we do this is that it facilitates now the exploration, because we can explore, our policy can be parameterized in terms of this Z. So we can explore new things in the space of Z, in the space of reasonable trajectories in the physical system, rather than trying to explore in terms of all possible trajectories that the robot is able to do. Also, it facilitates safety. If we have trained the system such that this encoder-decoder structure that we have only has shown, or we have only demonstrated here, safe trajectories, then the generator has learned to generate safe trajectories. So what the policy we want to then learn is just a single time instant mapping from the goal, or a start and go, to this latent space, Z, which is now, the start and goal is rather low dimensional, and the Z typically is also has only a couple of dimensions. So suddenly our learning problem from getting to 700 dimensional trajectory, suddenly we are maybe 3-dimensional latent system, or from 2 to 8-dimensional latent system that is able to describe the different situations. So of course we want, in order to learn this, we don't want to learn this only for particular condition. So this trajectory generator has to cover all the possible different environment conditions. So we have to learn the trajectories that are relevant or somehow meaningful across all those environment conditions. So it's not that we are only learning a trajectory for a single environment condition, but across them. And then basically that's the part. This is something that we did also early, or actually it's a kind of inspired by our work from last year. So the next part is the meta-learning. So this has simplified our problem quite a lot to do to turn it into a bandit and in a much lower dimensional space. But the idea we did here to do the meta-learning or meta-reinforcement learning relates to something called MAML. I think that quite many of you have probably at least heard it, but I'm trying to, because I wonder that probably not all of you know MAML, so I'm trying to give you a very quick introduction to MAML first before telling how it relates to our case. So MAML is a acronym for model-agnostic meta-learning, proposed a couple of years ago by people from Berkeley. And the idea there is that when we don't want to do model adaptation, we have to explicitly take into account that the model we learn will be adapted later. And the way we adapt our models in neural networks is typically gradient descent. So the idea is that if we have a model that we know will be later adapted with more data, We should not build a model that fits our current data best. We should build a model that is able to adapt the easiest. So basically, the model for which the performance after adaptation is the best possible one. That can be modeled in a rather simple way, such that if we think in the terms that we want to result in one of those three models in the end. We want to build a model for which, this is now the model that was built, this is the model parameters here. We want to build a model for which it's easiest to move to those new model parameters. We want to build a model that after making further adaptation steps, it will be as close as possible to those models we want to adapt to. And that can be modeled such that we want to minimize the loss of the model across the distribution. Now I'm taking my particular taus here, so basically over the distribution of taus. And this part here is the model for particular tau, the model after adaptation, where the model after adaptation is just the model we had, or the model we are optimizing, plus a gradient step. This is a single step. It basically says that we want to find a model that under the average of all these situations that we have, we want to consider after one gradient update. I mean, we will then extend this to several updates, but after one gradient update, it'll be as good as possible. And this is basically just the lower part here is just the standard gradient descent update. So we want to minimize the expected loss after the update. So this is the basic idea of MAML. So we want to get a model for after an update, it's as good as it possibly can be, under the expectation over the uncertain parameters, like the uncertain frictions we had here. So when we move it back to the original idea, so if we think in terms of the policy adaptation here, we want to learn a meta policy. And the meta policy is actually now a policy which tells us this is the model parameters that you use to first hit the puck with, to actually gather information of the friction. As well as we want the meta policy also includes things like in typical meta-learning idea is that we are learning the learning rule. So we are also adapting the gradient descent parameters, such as the step size. So we are learning a model that is good to learn or good to do the update for. So the single update then consists of repeating a few times, sampling and basically executing the actions with the meta policy, and then calculating the loss. This is just the typical loss of this is actually the gradient, or this is the loss function, and here we take the gradients that towards the loss functions. And we can do this a few times. So I expect that we are able to do a few hits with the real system and observe the results, do an update, do a few other more hits. This internal loop K is doing first 3 hits with the system to take into account the variability of the system or the stochastic dynamics. Do a single update and repeat these again a few times, maybe 2 or 3 more times, such that we get now with a very few data points from the real world, only observing where the puck went. In those cases, we are able to get a policy that then solves the problem. So the important thing is that here in the adaptation, we are adapting that model in a particular individual, only one physical condition, and we will, but we want it to be able to adapt across all the range of physical conditions we want to cover. So then, how to train this meta policy? So basically, how to train the starting point and the learning rule. So this is actually not very complex either. Because what we do is, if we can sample the task, we have the distribution of all the tasks, we do a sample-based method where we sample a particular task, we then perform this adaptation. So basically we run the adaptation algorithm and collect their data of how under this particular task the adaptation worked. And what we can do is we can calculate now the gradient of meta policy with respect to this adaptation step. So this basically will just mean that here we have the different goal states we have. These are the adaptive policies for each environment. These will generate us the trajectories. In this case, it just shows the simulation, but we run them on the robot. These are the loss updates we do for each policy individually, but then the loss of the meta policy can be now calculated in terms of gradients of these individual losses. So we can kind of back-propagate. This is actually in a way of back-propagating back to the outer loop of meta-learning, the gradients from the individual policy updates under the distribution of tasks we have. This is, you could think in terms of this kind of a hierarchical back-propagation plus some kind of a stochastic gradient descent scheme where this sampling here is then the meta-level stochasticity of the gradient descent. Okay, so in order to make it, okay, now I need to try to start the video, and let's see, very briefly, just, okay, let's see what we'll get out of this. Just to show, okay, the problem, this is what we want to get in the end, but let me feed forward because we are soon out of time. Okay, these are some latent space. So this is basically, we can run first the policy in simulation. We see that okay, this is what we can learn after adaptation, but let's just skip forward. So of course we want then to have different system here. One thing to point out here is that there are also other physical parameters that the simulation is not able to cope with. So that for that reason, we don't expect to learn everything, but we are able to have here a few different examples. This is basically before any adaptation, the robot will do just something to explore it. And this X shows here the varying goal location. And after the adaptation, we are able to, for different pucks which have very different frictions, learn. This is again before adaptation, and another example before adaptation with two different pucks. And after adaptation, we are able to get at least close to the optimal one. Okay, I'll skip the rest of the video if I'm able to close it somehow. Okay, so numeric results just to show you kind of, hopefully that works. So first of all, we wanted to have a baseline, and in typical way to address varying parameters is domain randomization. So you try to build a policy that works despite the variability in some parameters. If you do domain randomization, that basically means optimize the performance over the entire distribution. And initially that one of course works better. The brown one here is the domain randomized baseline, and initially it works better, but that hasn't been built for adaptation. And that means that after adaptation steps, the horizontal axis is the number of adaptation steps. We see that actually the model that has been built for adaptation works better, even though we have the same optimized gradient descent rule in both of them. The interesting thing here, though, is that actually when we do policy gradient updates for this domain randomized baseline policy, that sometimes, even though gradient descent is supposed to make you better, it actually starts to deteriorate the performance. So that even though we have now a starting point where we try to make a policy that works across the entire set of parameters, there are cases where after updating the policy, after gathering real data from an individual situation, the policy starts to deteriorate. And this is really something where we first thought it was a bug, but apparently it turned out it's not. So basically what happens is that when we have this part here on the left is the baseline domain randomization, and this is the meta-learning part, which explicitly takes into account that there are further graded updates. The point is that when we do domain randomization, the problem is that the model can start to move into regions which were unexplored in the data originally, because it didn't take into account the possibility that there is further adaptation that will be done. So that means that the policy starts to diverge from kind of known area of the space, and especially this relates to now the reason or the latent space. So we are diverging from the area where the latent space is well defined. And that means that for that reason we see that these are just different individual cases. So you could think that different sets of friction parameters, we see that those start to diverge, and they go pretty far from the 0, which is actually the place where the variational autoencoder tries to fit everything around the 0. I mean, with a 0 mean and unit variance. So the points that are far from that are points where actually the variational autoencoder is not very likely. It's those corner cases that the autoencoder is able to, or the decoder part is able to decode. While when we look at the case of the meta-learning, where these stay much closer together. So by taking explicitly into account the fact that there are further updates, regularizes the update. So this is actually something that has been in one paper last year, or one R6 paper, we found this afterwards, that there is similar thing in another context has been also proposed by some Berkeley people, or that they observed the same thing, that explicit consideration of those further updates or regularizes the policy better. So we get basically exactly the same thing also in real world that we had in simulation, is even surprisingly similar results. Usually it never happens that when you move from simulation to reality, you exactly see here for one of the parts we see exactly the same thing, that the baseline starts to deteriorate, and for another one which happens to be very close to the mean of the initial policy, it works initially much better, but in the end we get much better with adaptation. So to close, I want to have two, hopefully, if you follow this far, thought-provoking things as open questions. So this way we can kind of account for uncertainty in known dynamics parameters, but there are also other dynamics parameters and other dynamics uncertainties. So one thing we kind of observe here is that in some cases it's possible that the uncertainty we put in the system is able to account for other modeling uncertainties as well. In the sense that if you think that there are many sources of uncertainty in the system, at some point there are some effect. Maybe you could think in terms of central limit theorem that says that when you have lots of random effects, some effect of them starts to look like Gaussian. This is not the central limit theorem for sure. We are not in the number of effects and they are not identical for sure in this particular case. But in a similar way, we are able, if we are able to account for large number of different types of uncertainties, that seems to actually improve our tolerance to other kinds of uncertainties as well. And this would be extremely interesting theoretical problems to study as well. I'm not sure how to exactly formulate this, but we have seen it in different cases. I mean, it has been shown to actually work in vision. For example, when people do domain randomization for visual perception. So basically doing random textures or random noise in images and increasing tolerance. But in those examples, people have shown that it actually gives us tolerance to other kinds of uncertainties or unmodeled phenomena as well. Because these uncertainties kind of correlate with other types of uncertainties as well, and the sum effect of many types of uncertainties together kind of can capture the variability of real world better. So that's kind of my first point, or bigger point, that is not exactly related to this paper, but an observation based on the things we did. Another thing is, what we did is on-policy adaptation. So basically, we run the same policy that we are adapting. We run the policy and we are taking that same information from that policy and making a step from that policy to a new policy. But would a use of another separate exploration policy and off-policy adaptation allow faster adaptation? I'm pretty sure it would. At least it cannot be worse. I mean, by definition, if you have an optimal exploration policy, it cannot be. It must be at least as good as this policy we had. And very likely doing informed or active exploration by some kind of information theoretic or other construct that allows us to take into terms of how can we better gather information about the particular parameters. Here we didn't know exactly the parameter value, so we're not doing parameter estimation, we're just doing policy adaptation under the parameter uncertainty, but still being able to do better ways to explore, gather data from the exploration, and then do an update of a policy. So this is something that I have not seen anybody do, even in the case of MAML, and would be another very interesting thing to kind of combine the ideas of, let's say, informative exploration, plus then doing the idea of meta-learning, because you can then have another starting point that is given for the exploration policy and another starting point for the adaptation of the policy you would adapt. Gradient-based meta-learning is, of course, only one way of doing meta-learning. And the thing we are also looking forward now at other types of meta-learning in our more recent work after this one. Okay, that's all for today. I hope you could follow at least part of my presentation, and thank you. If there are any questions, I'd be happy to answer.
We have some 5 minutes for questions.
Yes.
One of your brilliant graduate students, Oliver, is working on an interesting project on the Trenox automated crane.
Mm-hmm.
How do you see your research in this new automation center helping Trenox, which is based here in Otaniemi, accelerate the adoption of their self-driving automated crane to meet the safety and regulatory requirements of their government? They have 2 clients right now, and this applied research would help Trenox grow. We'd be able to hire more people here. So the application is specifically an automated self-driving crane on large construction sites.
Okay, I think that the question is primarily about actually regulation, right? This actually, it's a
certification of
sure.
for this intended safety or the
yes, but I think that in that case it's still. I mean, the certification is based on regulation, and I wonder if it's the European machinery safety or machinery directive that covers the cranes, or I mean, for different domains there are typically domain-specific regulations about how the safety needs to be, or functional safety needs to be ensured. I'm not sure about this kind of tower cranes. What is the regulation that considers that particular domain? Because this is somehow domain-specific. Let's say for automated cars. I mean, or for vehicles, we have particular regulations that are very specific for those, and they are. So unfortunately, I'm not sure if I can.
So the question is, how can your research and this new automation
Sure.
help accelerate the testing and adoption? Because there's about 7 months, and the leading expert from the United States is going to be here to see if that technology is ready for scaling. There are about 100,000 cranes worldwide.
Sure.
So it's an immediate business case.
Sure.
So I'm looking very practical applications here.
Okay. So in your case, let's say the sense in sense of the center. I'm not the director of the center. Just to make a point here, but we are, at the moment, we are looking at some, with industry, at another use case which is pretty similar, and starting the, not yet the access time testing, but physical system testing. But unfortunately, because of confidentiality, I'm not able to, at least publicly, much talk about the details. So we are in sense of the center. I think the center provides expertise on, at the moment, not so much about the domain-specific regulations, which typically come from the particular company anyway, but about how, on which machine learning methods can be used as components such that they can be validated. So we have some expertise. It's not directly related to our research, but more about the work we've done to bring that research in practice in other domains. So I think that would be the ways that we can talk about these individual cases, but about your particular case, I cannot comment now.
Makes sense to continue this.
Sure.
Any other questions? So I have one which I, oh, sorry.
Thank you for the excellent presentation. I was thinking about what you said quite in the beginning, that you don't believe that end-to-end systems will solve the self-driving car problem. So, first of all, why not? And do you agree that there's room for deterministic logic in decision making, such as driving a car, or do you just deal with conflicts and fuzziness of the real world with something like stochastic flexibility?
Okay, if you allow me to be a bit philosophical, I would have a human brain without any connections. If you just have the computational capability of a human brain, but we wouldn't have any evolution behind it, I don't think in a human lifetime the brain would be able to learn to drive. So also, this is more about so that, I mean, from the point of view, I'm not claiming that end-to-end systems would not be able to, but I think that at the moment we are not able to train those systems to do that. Yes.
That's true for computer vision as well.
Sure.
Yeah, that's true for anything that neural networks are basically.
Sure, but in domains where we do have data, we have vast amounts of data, we are able to, we're not able to build semantics there, but we're able to build systems that can be used to, which are, let's say, close enough to human performance, not meaning that they do the same errors that humans do. They may do, in some sense, crazy errors for a human observer, but they may be able to do better than humans in other cases. So statistically, they may be, let's say, on par with human.
So where do you put the deterministic logic then, in high-level decision making?
If we are looking at safety, typically the safety is one thing where we want to be able to either deterministic logic or other logic level semantic places where we want to ensure what are the rules that this system will adhere to. I'm not sure if we all, at least those rules are specified in logic. I'm not sure if we are able to, these systems are stochastic. I don't think that we are able to, using deterministic logic, prove them, but probably probabilistic logic, let's say stochastically, we are able to show either with probabilistic logics or other ways. But I think that the rules need to be semantically meaningful for us to certify systems, for example. We're not able to certify systems, we're not able to take the systems in action, in practice, unless we understand what are the things that we verified about the system.
I think we are out of time, but Ville is based here, so you can read.
Yes.
Thanks a lot.